Fundamentally, an electromagnetic wave comes from the idea of self-sustaining fields. So if we think about the ways that we've now learned to induce electric and magnetic fields, if we have a changing magnetic field, just to start here, a changing magnetic field creates an electric field. But if this keeps changing in the correct way, this electric field can itself change. Once this electric field is changing, that induces a magnetic field, and so on. You get back to the changing magnetic field. So the point being that you can create this cycle where your electric fields are creating magnetic fields are creating electric fields, without actually having what we would call a source. We can have this happen without charges present, without currents present. Now, obviously, there has to be something that kicked off this whole thing, right? It can't just appear out of nowhere. However, once it's going, we could take away our source, so we could imagine this moving away from the source and the cycle continuing. So where this comes from mathematically are the Maxwell's equations. We call this version the source free. So what that means is that up here where we used to have Gauss's law, charge enclosed equals 0, which why this side is 0. Now this side was always 0, and our electric field here was created by a changing magnetic flux. Now our magnetic field, remember this was Ampere-Maxwell's law. Ampere's law said that there was some I through, but we're saying that this current equals 0. So saying that it's source free means that our enclosed charge is 0 and that the current going through a surface is 0. That's just saying that we have no charges and we have no currents. However, you still are left with these equations. These first two aren't actually very useful. However, these are particularly useful. And again, you see this relationship between E and M for magnetic, B and E. So this is how we're able to actually get these self-sustaining electric and magnetic fields, is based on these two equations. So what we end up with is going to be an electromagnetic wave, and we're going to initially think about it as a plane wave. Now remember that the plane wave itself is typically a simplification of many other scenarios, but mathematically is the simplest to deal with. So in our plane wave, we have a defined direction of propagation. So this just means that our wave is traveling in some direction, which in this case is x. So in this picture, our wave is traveling in x. Now, the idea of this being a plane wave is that our fields are equal along a plane perpendicular to travel. And so this plane here is this one. So this plane lives in the YZ plane, and that is how it's perpendicular to travel. And all we're saying here is that if you look at your electric field, the magnitude of that electric field is the same everywhere on that plane. And notice that that plane would continue in the Z direction and the Y direction. We, of course, only show a portion of it. The magnetic field also points with the same magnitude and direction every single spot on that plane. So we've shown 9 locations here, but remember the fields are defined for every point in space, and so the same magnitude and direction is true for any other spot on that plane. Now, a really important thing, which isn't true only for the plane waves, it's always true, is that our electric and our magnetic fields are perpendicular to one another. Now obviously this is trying to be a fancy 3D view, but there's a 90-degree angle between those. And notice that there's also a 90-degree angle between your electric field and your direction of propagation, and a 90-degree angle between your direction of propagation and the magnetic field. So basically this here is making a little cube for you, which I'm bad at drawing, but you have 3 90-degree angles there. So that's something we're going to come back to, and it's pretty important to be able to figure out the direction of electric fields, magnetic fields, and direction of propagation, and if you're given 2 of those, you should be able to figure out the third. So we'll come back to that in a little bit. Now, The next thing to realize about this is that this is a longitudinal wave. So our field strengths are going to vary along the direction of propagation, but since they are perpendicular to the direction of propagation, that's why we can say that this is a longitudinal wave. So as a function of x, our magnetic fields and our electric fields are actually changing in magnitude. However, notice that you still always have a right angle between B and E and between each of those field vectors and our direction of propagation. So in this picture, we're able to kind of see that as a function of x, our field strengths vary. Now remember that this is a plane wave, so in this plane, our field strengths are actually not varying, and that's why these three are equal. So this is only showing three that actually lie in a plane, but that would continue out equal in space. But then as we march that plane along in the x direction, you get different magnitudes of field. Now this is also going to be changing in time, but we don't necessarily show that. And you can think of this as a traveling wave. But of course, we've talked about lasers and the idea of having standing electromagnetic waves, but both traveling waves and standing waves, you would actually have this varying in time as well.